Right, so. Let's see, so I can. On the interval from. Five. In max. Fs equals. By the way, there has to be a critical number in between. You know how I can fill this so quickly. Write it in. Well, there's something more fundamental, more simple-minded, and that is, if I plug in 1/2 here, what's the exponent? 2 plus a half. If I plug in 2 here, the exponent is 2 plus a half. So the value of the function is the same at the two endpoints, right? So unless this function is flat, which it ain't, right, then there has to be a critical. And let's see what happens. And that was where you struggle to find the critical. Your first step here is correct, but it's not, you don't really need to go that far. Right? So let's take the derivative. What's the derivative of d to the blob? Blob. See, here I've got a constant base and variable exponent, so I'm good to go. Now I've got to multiply by the derivative of what I find upstairs, which in this case is because that's x minus 1 is derivative, negative x negative. So notice, of course, there's a problem here when x equals 0, but that does not affect us at all. Skipped over that. So there's no way that first term, the exponential term, this is neither 0 nor is it undefined. So the only critical business come out of here. Of course, x equals 0 is the point where that's undefined, but again, it's not our interval, so we're not going to worry about it. So this boils down to we need to solve this here. Get 1, or I get x squared is 1. So x is 1 negative. Again, negative 1 is not in our thing. So I've only got one critical. So only relevant critical number is x equals 1. So notice f of 2 is f 1/2. So there's the endpoints. So is e to the 5 halves. Let's get 2.5. And that's the critical number. I'm already going to tell you, it's going to be the minimum. If it's less than that, the maximum otherwise. I want to put in 1 here. I can 1 plus 1. So here's the min. Here's the max. On a small scale. Yeah, it's like this. Well, no, close to half. Any questions on?
I don't know. I was trying to take it down until you could take it down.
Like, yeah, it's very good, and I'm glad you got those skills, right? So just remember, if it's variable base and a constant exponent, there's an easier way. If there's a constant variable, I mean, I beat logs into my students so bad that if one year I did, that if I asked them to take a derivative, that's the first thing they do is pick a log. Don't do that. Just right through that step, right? Okay, other questions?
This is good.
And what is it? Is it log of x cubed minus 3x?
It was, yeah, excuse me.
What is it? Okay, well, we can look at that. That's- here. Let's go. Okay, good. So that's right. So, so we want to draw this function, we're going to graph this. And, the function at hand is natural log yeah, that will that's gonna apply. Well, it's going to be 3 times x squared minus 1 x cubed minus 3x. That's what the first bit's going to be anyway. And the other bit, the second derivative, is given to you also minus 3x4 minus 9 over x cubed minus 3x. With some squared, I guess. Now, in a certain sense, you won the lottery on the second derivative. It's like thinking about the second derivative. It's easy to analyze. I'm not even going to look at that after I make this observation.
So
It is always going to be negative.
I'm not either wrong, but
That is correct, because notice that thing, the biggest it can ever be at 0, and then you subtract 9 for it. You've got a negative top and a positive bottom, always. So this is always negative. This function concave down, game over, everywhere that you draw it. Oh, I like that. That made more. For this one, we need to sniff around and find the critical points. And what did you get?
plus minus one, plus minus square root of 3.
Right. And I'm going to put plus or minus square root of 3 and 0 down here in red. Because plus or minus 1, I've got a zero slope tangent, so I expect to move the horizontal tangent line. Here, I've got plenty of business. And for these two, the numbers plus or minus radical 3 and 0 are not in the domain of the function, because you actually get log 0 instead of this. In fact, what do you expect might happen in these 3 points? What do you expect is going on? Well, for example, what happens? Let's kind of break this apart. We want to be more explicit. X. When you get very, very close to 0, this thing, well, its absolute value is always positive. So this is getting very small. The log is going negative then, right? I expect there to be an action. Same with plus radical 3 and minus Just making- Yeah, so I expect maybe vertical asymptotes at these three red ones. Let's see how it pans out.
Whatever reason I see. So then when you were asking, what do you think these three points are, you want to spread plus or minus? I was thinking.
Yeah, but then you take a log of it. Right, so that's right. And so it's getting very, very close to zero, but you're taking log of that. Now remember, let me do a picture of log x. And actually, let me do this. This is natural log of the absolute value of x. The log is very small, or I'm sorry, when the argument of log is very small, then the logarithm is very, very large. Right, it's very large and negative. So that's why, so here you're getting very, very close to zero, near actually to zero. I expect a large log. I expect to go negative infinity. And same when you get close to radical 3 and minus radical 3. Is that clear enough? Okay, so this is what's going on. We got a lot of things to put on there with the current line here. All right. What happens to this animal when x is very, very large, say 100? Positive, positive, being very large. What happens when you're between 1 and radical 3, right? Like maybe 1.1. Well, that's negative. Well, I guess we'll do no words. So well, 0. Right. So we know actually. Oh, I looked at the wrong thing. Yeah. Freaking out here. In the back office. I'm looking at that prime. I should be looking at this thing right here. All right. Let me write this out a little bit more, maybe that'll help. Okay, let's try this again. What happens when you're beyond right? Like 10? Positive top, positive top. Everybody. What happens if you're in this range here, like 1.1? You have a positive top, that's a little bit bigger than 1. But right, this is going to be less than, this is going to be a negative here, and that's going to be positive and negative. Grand total thing. Right, okay. How about between 0 and 1, something like a half? Well, that's going to be a negative. That's going to be a negative, and that's a positive. Two negatives. I expect these to reverse themselves. So what if you have negative a half? Again, negative, negative, and now that's negative. Negative, positive. Everybody okay? How about something like minus 1.1? Now that's going to be a little bit bigger one. So this is going to be positive. That's going to be negative, negative. And finally, what happens if you have negative huge? That's going to be positive, positive, negative.
But because it's odd, is it safe to assume that it would just be the opposite on the other side, or is that crazy?
Well, this function is actually, this function is actually even, not odd. Right, so something like, cosine x, but that is why the first. Right, but you know, that's kind of a good gut check, but there's weird things that can happen. Yes, it's true that this will always happen if it's an even function. You can't guarantee it. So F decreases, increases, decreases, decreases, increases, decreases. And this, well, what happens here? Up, down, local max. How about this? It's also. Plugging that function there. What about a 0? Ooh, tricky. Can't plug 0 in, it's local money. I expect that to be my yes. In a quick gut check is go try to plug 0 in, that's doesn't work. So I expect these three right here are asymptotes, and the function is always concave down. Right, so whatever I draw is always unhappy. So let's see what I've got here. 1 log 2, so maybe it's like that. It's a local max. Local max. Radical 3, say, I expect 3 to be an asymptote. Plus and minus radical 3, that is. Let's go up to this asymptote. It's always decreasing and it's always concave. Something like that, perhaps. Okay. What happens in this range? So this is from radical 3, negative radical 3, 1, negative 1, 1, 3. What happens from radical 3 over an aspect of snow and aspect 2? Let's see, it increases up to the local max, and then it decreases down here, always being in half. So I expect to do something like this. Always concave down. On the other side, it increases off the asymptote. So it hits the max and goes down. 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 And then on the other side, concave down and it's always. Yes.
So if you're finding the local maxes, how come you didn't do it for square? Like from that line, square three, for the negative square three, where it's negative positive, how do you say that's?
What happens when you plug in radical 3 here? When you get log of 0, which doesn't exist. That's a big giveaway right there. Radical 3 is not even in the domain. And that's why I knew there was something. So when it's not in the domain of the function, it might be a whole, or it might be an asymptote, vertical asymptote, or other. Here. Okay. By the way, what do you, no, good questions. Hard to go on. How many times that thing cross the axis?
across six.
you know, where it crosses the axis. It's not anything nice. The way that you find it is, it's where x cubed. Right, because the log of one is 0, right? X cubed minus 3x is 1, so that's where, well, wait a minute. That only gives 3 places where it crosses the axis. Because remember, a cubic polynomial can have at most 3 real solutions, right? Like, where the other 3 go? Remember, this is absolute value here. So you might also have x cubed minus 3x equals -1. Right? And if that's -1, it's absolute value. So that's where solving the equation get you across the axis, but it's not really worth it not to do it.
Like I'm just. Well, just keep working.
So what, before we move off of this one, what are the pieces that you think are kind of missing for you here?
You definitely recognize that those being asymptotes.
Well, you know, the mathematician in you, so you can have asymptotes in the function exists there. For example, you can have a function like this. Right, but for the kind of functions that you have here, the compositions and things like this, it's hard to get something. Right. How about this? And see if I can figure out a way to do this. Well, actually, let's do this. I think we talked about it before, but someone heard it. That should. Yeah. Just my list. I might just use the first group. We'll see how lazy I am. This is t to the 1 over x plus x times the derivative upstairs. In fact, we just did this with that other problem. Let's persevere and see what we get. This times the derivative of this, which is 2 over x cubed. Because the derivative of 1 is 0, and this is minus 2x minus 2, or minus x minus 2. Plus this times the derivative of this, but I already did this. So that's e to the 1 over x times minus 1 over x squared. That's the second derivative. At least if I clean this up a little bit, make it reasonable to use. This is 2 over x cubed minus 1 over x squared. That's 1. Oh, oops. That's 1 over x squared. So I pull this out. I've got to square this. That's going to be plus 1 over x4 minus 2 over x squared plus 1. which is this is x4 common denominator. This will be x4 minus 2x squared plus 2x plus 1 so basically that's x squared plus 1 minus squared plus 2x. I'm not gonna care about having that, because the question is now where the inverse points this. This is easy, it's just 0. This is easy, it's just well, this is an exponential, it's 0. So you've got x equals 0, and now you've got to find where this is positive or negative. So I can do a separate problem by figuring out what this looks like, and then try to find where it's above and below, or where it's 0. But actually, I'm not going to bother. Down here. Maybe we will be. So if we look at the first derivative on so I'm going to draw a sketch that's based on the first derivative. This is the first derivative. And the critical numbers for this are plus or minus 1. Right? And also x equals 0, which technically isn't a critical number because the function is not found there, but let's see what this thing does. Notice this piece, the exponential piece, always positive. X squared piece is always positive. So the sign of this animal between only by the x squared minus 1. It's positive, and this thing is positive, it's negative, it's negative. So it's like negative in between and positive outside. So it decreases, no, decreases, decreases, decreases. And so minus 1 is going to both max. Minus 1. Let's see, this would be e to the minus 2. And down up, let's say local min at 1 squared. That was actually it. And again, it's kind of weird, right? Because the max is man, what are you supposed to happen to 0? Zero is a little bit in the following sense. This is one of the utilitarian things about limits. Is what's going. What happens next is very, very here's everybody remember the e to the x looks like this. I'm going to use that as 2. Now, what happens is it's very, very close to 0 from the positive side. This x piece getting close to 0, right? So it's negative. This piece is getting what about 1 over x? It's getting huge positive, right? So the exponent here, that's almost 0. This is getting huge positive. The exponent of the exponential is going to infinity. Agree? Look at e to the x. That means this thing is going to infinity. Everybody okay? What happens when you go to the other side? Now you're getting close to zero, but you're tiny to the negative. Again, that's almost zero, it's negative. But now the huge number is what? It's a huge negative number. So the exponent here is going to be negative infinity. What's that? Zero. So in this function, it's a little bit funky what happens because you've got the slope of max -1 e to the -2, which is positive. And we get a local min over here on this side of 1 in e squared, which is bigger than this. Now let's look at what happens off of this. As x goes to 0 from the positive side, it's going to infinity, right? So you're going to infinity here. So that means it should be coming off the asymptote. Okay, it's decreasing. That's good. We didn't do anything with concavity, but after this, it increases pretty rapidly, actually. What happens here? Well, it increases up to local max, and then it decreases and it goes to 0. That's the receipt. Okay, let's see what happens to okay. By the way, let's put another one. Remember, this is the polynomial we had to find roots of, more than the concavity of this. But I was too lazy to do it. Let's see how hard that is to do. Well, let me ask you this. My picture still looking. See how it does that little kind of little pump into there? Well, the first thing could do several things. That. Or it could do the way I drew it, like that. I didn't check it on cabin. How can I tell which one of those is the most realistic? What's one thing I could do? What's it? Well, see here, what's true is the concavity always seems to be down here. It's even more extreme here, right? But here, the way I drew it is I changed the concavity from down to up last minute, right? How can we pick which one of these is the most realistic? Besides concavity, can you tell me something that's different about the derivative here? As you get closer and closer to the open hole, what does it look like the derivative is getting closer to here? 0, because it's flattening out. Here it's getting closer to some number like maybe -7. Here it might be -infinity, right? Let's check it out. Let's see which one of these is more realistic. Really what we have to do is this. Let's look at the limit. As x goes to 0 to the negative side, because that's where we're going. Of e speeds. Now, I've already figured out the limit. This limit is 0, right? And this is -1. So you get 0 top, 0 on the bottom. I'm going to do L'Hopital's rule, but I don't want to do L'Hopital's rule. Why? Well, nobody wants to take the risk of the product, right? And in fact, I think it's better this way. Let's do this. This is the limit. X goes to 0 minus e to the x times e to the 1 over x times x squared minus 1 over x squared. And what I'm going to do is I'm going to get rid of all the stuff that's an offender. As x goes to 0, where does e to the x go? It goes to 1. It's not doing anything wrong. How about x squared minus 1? It's going to negative. This is the piece that is going to negative infinity, or I'm sorry, 0, and this is going to 0. Well, so so let's just look. Propofol will make this worse. You see why? Let's do one step. Derivative of e to the 1 over x, e to the 1 over x minus 1 over x squared. Derivative of x squared is 2x. And so when I clean this all up, lim as x goes to 0, e to the 1 over x over the negative 2x cubed. And now I've gone from the 2 power to the 3 power. This is not working well. Okay, how else might I do this? So, well, let me, again, I'm gonna let the alpha go down. The first thing we'll do, I'm gonna do this trick here that I talked about. What I'm gonna do is the x squared is nice to it's derivative to a. This is worse because it spits out a negative power that's bigger than to start with, right? It starts to grow. So let's do this. Let's let t equal 1 over x. So I'm going to have to limit e t and x is 1 over t. 1 over t squared. Place x by 1 over t and so. You okay with that? Now, here's the problem though. Originally x is going to 0. So where's t going? If x is going to 0 from the negative side, where's t going? It's going to negative. Right? This is limit as t goes to negative infinity t squared t. And this is an infinity times 0 situation. Right? But here, I'm going to put the exponential bottom. This is lim as t goes to negative infinity of t squared over e to the negative wrote it as fractions, so I can look, oh. Right, this is infinity over infinity. Two t over minus e minus t. The derivative that is doing in capacity. But I still get negative infinity over negative infinity. Solve it one more time. And I get 2 over e minus d. And now I have 2 over infinity, so I can see that. Actually, that shows that I guessed right. This is sort of a realistic picture because the tangent line should flatten down to 0. Right? That's what this says. But it's a complicated trick, but tangent line flatten down to 0. That means, by the way, that means there has to be a concavity check. So even though I didn't figure out what the concavity was on this, I know that somewhere between here, where you've got the local max, and down here, because it flattens out to 0, there's going to be concavity. Okay. Questions? Okay, what else we got? Oh, is this sine 3x?
I was looking out. Like I need one or two.
All right, so it's sine squared 3x. So let's do this here. Sounds very right. It should be 3, I think. Okay, so the first thing to do with any fluid problem, put your eyeballs on it and try to plug in and see what they say. I mean, if I get 2 over 7, I'm done. Right? Well, no surprise if I get 0. Right? So that's voices from on high telling you that there's more work. Okay, so let's go through this. What's the first thing that I come to? Right. So in case there's any confusion, this is sine of 3x all squared. Right. So that should be 2 sine 3x times let's see. 2 block apart times the derivative of what's inside. The derivative sine of block is cosine of block. Now go inside that. How about the other piece? The other piece is a little easier. I think it is derivative sine is cosine. I'm derivative of what's inside. Right, okay. And you know what? So let me clean this a little bit. When x goes to 0, notice there's 2, 3, and 6, so I'll cancel that. It's sine 3x, cosine 3x, cosine 3x squared, and Now, if you're go ahead and plug in, you get 0, 0 again, right? So you look total, but nobody wants to do this crap because it's the problem. Let me show you a shortcut. One of the things that you learn about limits early on is the product. The limit of a product of two things, this or this, times this or this, is limit second, as long as both limits exist. Now, when I plug in the 0, I get 0 from sine 3x, but I get 1 here. This isn't messing with anybody's crap, right? It's behaving itself. When I plug in 0 here, I get 0, and here again, I get 1. Let's take these two out of it, because I don't want to be taking their derivatives. They're not messing with me anyway. So as an aside, let's just look at that. It's much simpler. 0 from 0 to what we call rule. This is 3 cosine 3x over 1. It's my answer. So when I go back and put it together, this is 3, this is 1. Now, you don't have to do that. You can do what's helpful in probably here and here, but it's much more likely that you're going to make mistakes in one place. It's much more easy to sort of peel out the offenders and do the thing second. Now, word of warning, if we've gotten this limit doesn't exist, then that's trouble. Because the only way that you can break this up is both limits exist. So you have to massage it so they all exist. Any questions? Okay, other questions? So, Faith, did that clear it up for you? Okay. Okay, we catch up to what? All 2014, 72, and 16. 260. Fall 2014 exam 2, is that correct? And this is problem which? Three. Oh, holy buckets. This is like the log of the absolute value, the log of the absolute value of x, right? All right, let's take this apart. Log of the absolute value, the log of the absolute value of x. Okay. By the way, what's the domain of this? Okay, let's go the other way on this. What can you not plug in? Okay, so zero's out. because you can't plug it in here. And also, plus or minus one is out. Anybody come to mind? It's zero. That's exactly the point, right? If you put in one or minus one here, you get log of one, which is zero. And then you try to take another log, you're in trouble. But other than that, good. As long as you don't get zero in here or zero in here, you ought to be good, because whatever number you get, you're taking the absolute value of it and then you big log. Right? So, what do you suppose happens at zero? I think at zero, this thing is, so let me think about this for a moment. Is x is getting close to zero, the log is getting close to negative infinity. So the absolute value of that is going to infinity, log is infinity. I think we get a vertical asymptote of zero. And if I get one here, log zero, I think I get a vertical asymptote. Well, that's what it's looking like to me. Let's see what the derivatives tell us. The first derivative of this is given to you is called this f of x. F of x is, and we will assume in this problem I did this right, is 1 over x natural log x. Yeah. And the second derivative I got to be at natural log of the absolute value of x plus 1 over some other crap, x natural log absolute value of x all upon the square. Okay, that appears to be what I got from my first two derivatives. Oh, yeah, that's the point, isn't it? Yes, that's right. And hopefully I would have caught that when all my concatenating first, but let's make sure we get this right. That's negative. Clear. All right. I guess we need to start figuring out what's what. What are the trouble points for this? Well, there's no way you're making that numerator 0, it's 1, right? You can make the denominator undefined at 0, or at 0, it's also, yeah, this is great. And also plus or minus 1, you get 0 log, so let me write this in red because they're not critical numbers. These are the point where the asymptotes are, I think. What about concavity? Well, I'm going to get the same list of thugs right here that are make this 0. We got these bad boys right here, but we also can make the numerator 0 here. Let's see. Do I know what this is? Well, let us. Let me also point out that, of course, 0 is also sort of critical to this as well. Fine. We've already got that. Let's set this equal 0. So absolute value of X is E minus one, or one over E. And so X is plus or minus. So I get these more interesting ones popped up in concavity. Minus one over E and one over E. Okay, so let's look at the first derivative. Minus one, 0, 1. And these are my big offenders. They're not even in the domain function. Let's see what happens. Of course, the top here is always, so we just need the bottom of the sign. Well, let's see. Oh, you know what? I actually did overlook something. But did I? Let me see what here. Oh, right. Okay. I didn't. Let's suppose that X is bigger than 1, say 2. This is 2 is positive, log 2 is positive, so everything's positive. Let's suppose X is between 0 and 1. What do you know about the log of something that's between 0 and 1? It's negative. That's right. So if you get something like a half, it's positive, negative, so it's negative here. How about something between 0 and minus 1, something like minus a half? Well, again, you've got a log of 1/2. It's the absolute value strips back half. You got the negative, but now the 1/2 is negative. So it's positive here. And what happens if you're less than -1, say -2? The log of 2 is positive, negative is negative. So my function decreases, increases, decreases, increases. And there aren't any local extremes for this one, because all those points, none of them are in the domain of the function. There is no local min or local max. You draw them in asymptotes. Let's see what the second derivative says to me. Let's go -1, -1 over E, 0, 1 over E, 1. Okay. Oh, this helps. That denominator is always positive, so I don't even have to consider it. Right? It's always going to make it positive, not confusion. And let's not forget that. What's that? That's exactly right. This is squared. And let us know if it's negative, but I almost got earlier. Be careful about that. Notice that the places where log x plus 1, 0 are 1 over E and -1 over E and 1 over E. So when X is bigger than this, 1 over E, the log is bigger than 1, and so it's positive, but don't get negative. So it should be negative. Also, when X is less than -E, then again, you take the absolute value, the log is bigger than 1. So that should be positive, don't get negative. And in between the 1 over E and -1 over E, this number is actually less than 1. So when you have this is actually going to be a negative number. And so again, these points are kind of red herrings, but here you got 2 points of deflection. And actually doesn't make any difference. So at E, a 1/e, if log is -1 is right. So plus or minus 1/e equals 0 or points reflection. It's not capital changes. I did that right. That's log of that is -1. That's -1. So let's see if I can draw this at all. I suspect that 0 here is, let's see, as we get closer and closer to 0, the log goes to negative infinity, absolute value positive infinity, the log is going to infinity. So I expect it actually to be, the log goes to plus infinity. Here's one negative. So let's try to do this here with between the asymptote of 0 and 1. As you get closer and closer, the log should get huge because of the absolute value. Off the asymptote, it's decreasing, and its concavity is positive until it's negative, and then it decreases the other one. So it's one of these units, so probably something like this. Right, concavity change there. There's not 1 and 0. And on this side, between -1 and 0, you get sort of a mirror image. It should increase toward the asymptote. It should increase off the asymptote like this and have a concavity change. It should go from down to up. Sort of the mirror image going here. That's what it should look like in the middle. Notice as you get close to plus or -1, this is getting close to 0. And log is negative infinity, so it should go negative infinity. These asymptotes should push down. As opposed to this one approaches up. We'll see. It's decreasing. And it's always kind of a big thing. So off the other side. And off the other side should be increasing. Okay with that? We'll just see how we did that now. By the way, you know what these points are, because if I've drawn this right, it should cross the axis here and here. Can you figure out the other 2 points? It crosses the x-axis 1/e and -1/e. Let's see where it's the other place it crosses.
So you took your property.
Yeah, because it's in the appropriate area. You said, you know what the x coordinates of the other 2 points what crosses the x axis is? Once I have one. Well, 1/e worked. We kind of figured that out on the fly because the log of 1/e is -1. You take the absolute value, and you get log one, you get zero, that's why it's the axis. That's when x is one over it. What else would work? How about x equals e? Right, then the log of e is one, and then the asymptote's already one. So this should be e is negative. Okay, any questions? If you struggle drawing these things too, and you know, for example, there's a point of inflection, you can write that on your drawing, right? Yeah, if you watch me do this, I do the ups and downs pretty good, but sometimes the point of inflection is hard to see, right? Where is it exactly that tangents go under and over, you know? So, you know, if you just kind of fudge what on there, so it makes it, just show me that you know what should happen. Oh, yeah, that's potential material, stuff out of that section, right? There's not a lot of kind of problems, right there. The big things, the big theorem in that section really was, let me ask you this. Suppose I walk up to you on the street and I give you a function on an interval. And you know that the derivative of the function on that interval is zero. What can you say about that? It's constant. That's exactly right. It's a horizontal line. Right? You know the derivative of constant zero. One of the consequences of Rawls' theorem and the mean value theorem is if the derivative is zero, it has to be constant. It's certainly clear that if it's constant, the derivative is zero. But the other way is true. And a corollary we had is if we had two functions, I don't know, f and g, and you took the derivative of f and you take the derivative of g, you get the same thing. That means f and g differ by a constant. Right? But yeah, it wouldn't hurt to do a similar theorem. You should know the statement of mean value theorem. Actually, if you know the statement of the mean value theorem, you know Rawls' theorem, because Rawls' theorem is just the mean value theorem where the two endpoints have the same line. That's it. Oh, is this long one you all? Other questions? Another good piece of advice I can give you is another big piece of this we have was maximating a continuous function on a closed interval. If you screw that up somehow, you can't quite get the right answer, just explain to me what you would have done, right? And you'll get some explain to me, show me on your test that you know what the process is. Sorry, number 6 on the same thing. Yeah. Oh, okay, this is the second one. Find the maximum and minimum values of function f of x. It is cosine 2ax. On the interval from here, 8 to 0. On the interval from 0 to okay. Why did I say a is bigger than 0? What does that function look like if a equals 0? Well, but it's very boring, isn't it, right? Because that would be sine 0, which is 0, and it's because cosine 0, which is 1. And you're, and that needs clarification for sure, if you're going to divide by a, right? So here we're taking a to be a positive number. Yeah, and also I want to be positive so that the power of a is actually bigger than 0. All right, so now got a continuous function, got a closed interval. So what's the first step? Take the derivative. That's exactly right. Let's get everything sorted out here. Well, let's see. Derivative of cosine is negative sine times the derivative of blob, which is 2a. Right. Was derivative 2ax is 2a. Derivative of sine is cosine blob. Derivative of sine, which is a. Now the eighth one, they're not at all. Okay, we've got the derivative. So now, what do we got the derivative for? What are we hunting for? Right, and for this one, with the cosines and the sines, there's never going to be a place where it's undefined. So we're just looking for places where this is 0, and in fact, there's actually quite infinitely many places for 0, but we only need them between here and here. All right. So let's do this. Let's set this equal to 0. What's the first thing to do? A is not 0, so I can divide outright, right? That makes my life a little bit easier. Okay, that's some progress. But now what? At this point, given the way I wrote this test, probably should raise your hand. You think this test, you can ask the fingers. What could I give you at this point? That's right. Right. Notice that my angle is different than my angle here, which is obnoxious. I gotta kind of get it all together here. But I can replace this with 2 sine AX cosine AX. Focus. All right, you see something I can strategize what I do with the next bit. I seem to have a common factor. Let's put cosine AX out there. And that's going to leave me here with -4 sine AX. That's going to leave me in circles. Everybody okay so far? Okay, so. This comes, this is 0, so I've got to solve this. And the other possibility is, but okay, so how do we solve this? Where's the cosine equal to 0? Now notice my angle can't be negative because I started at 0. Right? Where's the first place that the cosine is 0? At what angle? Right, over 2. So if AX is over 2, that's a possibility. What's the next place? Yeah, it's another 2 pi, so it's like 5 pi over 2, I guess. And so forth and so on. Right? But all of these are necessary. I get X is pi over 2a, 5 pi over 2a, and this is already too big, right? Because that's 2.5 times the head. This is 1/2 of the end, right? This is halfway across. But these are all too big. So I've got a test. So let me gather up the stuff I'm testing. X equals pi over 2a. And then how about this? For the other one, I've got a test. Sine AX is 1/4, right? That means that AX is the inverse sine of 1/4. where the sign is about 1/4 of the same. So it's like, let's start like this. And the next place that it's 1/4 is over here. So the first two is and then there's more that needs to be. So I get X is sine inverse 1/4 over A. Pi over A minus inverse sine 1/4 over A. And the rest of it's big, but now you're ready. I didn't divide by sign. I took the inverse function. All right, it's the inverse sine. Like we're going to your calculator, you know, the inverse sine function turns the angle. Angle here, so I need 1/8. So let's try to test this. And then of course I have to test the inverse. One over A inverse sine 4 pi minus pi over A minus 1 over A sine inverse 4. And then the endpoints, which are 0 pi over A. All right, let's test. Let's test them first. They'll be easier. F of 0. Cosine of 0, which is 1. Sine 0, which is 0. So F pi over A. When I replace X by pi over A, I get cosine of 2 pi, which is 1. Sine pi is 0. So also get 1 is this. Now, see what it is halfway across. Everywhere I see an X, I'm going to put in a pi over 2A. So that's going to be cosine of pi plus sine of pi over 2. So that's minus 1 plus 1 is 0. Whatever. Okay. Now, how am I going to do this other one? Well, the other one I've got, let's do F of 1 over A inverse sine. That's a taller order. See, do this. Let me also write this way. Let's see, cosine 2x. This is you all recognize that trick, didn't you? That's another one you can ask for. All right, all it is, I replace the cosine 2ax this is. And then the other pieces. Right, okay? Now, here's kind of the cool thing about this, because this looks awful, doesn't it? But it's not so bad. The following reason. Let's see. Yeah, I'll go. Notice that sine AX is 1/4. Right? Because that's where we got this. So I don't really have to plug this in. This piece is 1/4, and this is 1/4 squared. And what's the cosine of this? Well, you can do it this way. Cosine squared AX plus sine squared AX is always equal to 1. So in this case, if sine of AX is 1/4, then cosine squared AX plus 1/16 is 1. So cosine squared AX is 15/16. So if you do this right here, what you're going to get is this is going to be cosine squared AX, which is 15/16, minus sine squared of AX, which is 1/16, plus sine of AX, which is 1/4. So this comes to, that's like 4/16, 3. I get 18/16, so like 9/8. Everybody okay with that? And the only thing left, I guess, is this I over A minus. That's quite the same thing. So let's try this. Finally, suppose X is I over A minus 1/A inverse sine of 4. This means that AX is pi minus inverse sine 1/4. So all I need is cosine AX, sine AX. So sine AX is sine of this mess. Which is sine, which is 0, minus cosine. Sine. And cosine AX, this range still should be. Cosine squared AX. So just doing this again, so I get the same value here. Cosine squared minus sine squared. Over A minus 1/A inverse sine 4. Should also be 9/8. So it looks like the minimum is 0 on that interval, and the maximum is 9/8. Any questions? So this is an exercise of trigonometry, which I will give you free. Also, I've also done solid control days, and I'll let you use calculators too. But calculators, sometimes it's easier to do things this way. So don't depend on that. You should use a scientific calculator. You should graph this. How many of you have a graphing calculator? Just out of curiosity. Yeah, years ago, it was like all the rage to have this class, but I think it's not as popular as it used to be. And the graphic on the screens is really good. And actually, the technology has changed for everything in our society, except the graphic out. Things online. Better. Okay, what else we got? So is a 3 o'clock help session problematic for you? Okay. Yes. 2A, please. All righty. Okay. Oh, is this the X to the 7/3 minus 28 X to 1/3? So we'll just couple of things here. That'll help. I think it'll be easier to compute than this last one. X to the 7/3 minus 28 X to 2/3. I usually don't give you derivatives in these problems, so when you take the derivatives, be careful. Make sure you get it right. That last step, I don't really need, except when I actually do the comparison and I do the max min part, it might help here. And we're supposed to find the max. We're looking for the maximum min on the interval from -1 to 5. Okay, maximum is that. Okay, this is a continuous function, closed interval, so should be at least. Let's take a derivative of this carefully. 7/3 X to the 4/3 minus 28/3. Everybody agree so far? Then that's pretty up in the first step. Right. So now, again, kind of from computational focus, I think it's most convenient to pull this out. I like pulling out the biggest, fattest negative. The 7/3 is stripped out of this, and it jacks up the power of this by 2/3. Now 6/3 squared. This seems to be a -4, and then you can always multiply back to check yourself. And 7/3 X to the 4/3, 28/3 is. Right. And I like this form because it makes picking out critical numbers almost immediate. Which of these, does everybody see where I got all my critical numbers in the first place? All right. Which are relevant to the problem at hand? Zero and +2. So this -2 is not in my range. So this one's unnecessary. So now we're in a situation where all we have to do is have a contest. Biggest is the max, smallest is the min. And who's entered in the contest? Critical numbers we found that are relevant, and the index. And remember, folks, please, you're plugging these back into the function. Don't plug them back into the grid, because you'll just get garbage. And in fact, your critical number here, you get 0 or undefined. With the critical number. I'm plugging 0 to function, I totally get 0. Let's go back. When I put 2 in here, I get cube root of 2, and that's 4 minus 28, so I get minus 24 times 2 to the 1/3. When I plug in -1, I get a negative here. I get 1 minus 27, or 1 minus 28 minus 27, that's positive 27. And finally, and this is the last source of controversy, when I plug in 5, I get 5 to the 1/3 times 25 out of 28 is -3. It's 5 to the 1/3. Now, can you tell me? Okay, here's the easy part. Who wins the contest is max. This one's a clear winner because it's the only positive. So max. Everybody agree with that? And 0 is out of the contest because these two are negative. So the only question now is which one is smaller. Can you tell me which one is the smallest? Well, approximations, ballparks, very good reasons. I think you all have to agree that this is less than -24. Right, but it's -24 times something. And this thing's bigger than 1. All right. On the other hand, this thing right here is this is smaller than 2. Right, so this is greater than -6. Right, because -3 times 2 is -6. -3 times less than that, that's bigger than -6. So this is in a certain sense a smaller negative. This one's the net, then the curve rate. And of course, you know, a calculator will tell you that more definitively, but it's always going to be less.
How come we never use the same equation?
Oh, you can find where this is 0 or undefined if you like, but it's much harder to do. I factored this out. This and this, they're the same thing, they're just written in different forms. And this allows me to pick out, okay, 0 is a problem here, and plus or minus 2 make this equal.
Yeah. I asked the question. For the context, when we're putting numbers back, we got a special that we only use the right side of the top of the maps.
Oh, this one, just because it's easier, you'll get the same answer. It'll just look more confusing. Yeah, it'll just look like a mess. That's why I pull that out. It's just easier to mix it. Okay. Questions? Okay, what else we got? Yeah, you can use a sign. You need numbers or whatever, but you know, you can always ask me if you want to know like values and trig functions. So what what's the sign power says. And I'll give you any tree at the end of me, except for sine squared x, because sine squared x. And I'll give that to you too, but I'll charge you. Yes. Oh. Is it big here? I know. Okay, it's this one, well, 16, 15. Real range. 48. That's so weird. So there was two things. So what's this is all just numeric. This is supposed to be 2 squared. Right, which is funny because 3 times 2 is 3 times 4, which is 12, 60, 50. So I thought you got the digits turned around. It's supposed to be 15. But you turn that 2 into a 2 squared, and you actually got the right answer. Right, it reversed the digits. There you go. Okay, other questions?
Okay, can I have a question?
Sure.
Can you remind me?
Oh. Actually, that can be a deep question. The kind of functions you're looking at. So. Well, okay, so what do you need to have half plug X in, makes sense? You need couple things to happen. You need two x minus five be greater than zero. Right? Why not greater than or equal to zero? Why do I have to really honestly be bigger?
Is it because it's?
Well, it's because it's in the denominator. Because if two x plus five equals zero, then you've got a zero in the denominator. If that if that square root of two x plus minus five is on top, that will be greater than or equal. I need this to happen. Also, I need x squared minus one to be greater than zero as well. Because it's in the argument below. So let's see, what does this mean? So I need two x minus five bigger than zero and x squared is strictly bigger than one. We'll see what this means. Let me solve this. The first condition here means that x is greater than 5. Great. And the second condition is a little tricky. What does it mean for x squared to be greater than 1? It means x is bigger than 1, or x is less than minus 1. Because if it's a large enough negative, it's bigger. So let's see what are the regions of validity. This 5 halves, the x to be bigger than 5 halves. Like this. So for this one, bigger than this or smaller. Now you need this to happen and this to happen. So can you tell me what the region of validity is here? No, it's more restricted than that because you need to have both these things that happen. So for example, -2 works here, but it doesn't work here. But anything 5 halves is bigger, 5 halves is over here. So it's actually, this is the region of validity. Domain is x is bigger than 5 halves. That makes that denominator, it makes what's under the square root okay. It makes the denominator big, not 0. And it also happens to work with this. So basically what you do in find the domain, you're trying to find every value of x that you can plug in. So you don't want negatives in the square roots. You don't want zeros in the denominators. You don't want zeros in the argument of log. You don't want pi over 2 in the argument of things. Yes. Two on quiz. Oh. Consider the function express x squared. Okay, there's something I'm glad you asked. So g of x plus. Right, and first two derivatives are x 2x plus 16 squared from x 2 plus 32 over Okay, so let's go through it. By the way, superintendent, which white blood square was. It's like our old friend the parabola. What this function is x squared equals 16 of bracket, right? That is a single fraction. When x is very, very large, let's say x is a million. This is almost zero, right? And so what this means is, and in fact, this function is undefined at zero. It's probably got a vertical aspect. But this function can do all kinds of crazy stuff in here. But after a while, it settles down and yeah, it settles down. It gets very, very close. So behavior is wacky in the middle, but it gets more and more like parabola. It's actually it's very, very large. This is almost like x squared. Okay, so that's just something to keep in mind as we move forward. Okay, let's find critical numbers. I'm tempted to say zero, but of course zero is not in the domain. Domain is everything except. So now that we've gotten that business out of the way, let's set this equal to zero. So I get 2x cubed minus 16 equals 0, x cubed equals 8, and x equals 2. So this is critical. So let's look at the first derivative. I don't really have to factor anything. You can put this over a single denominator and evaluate it that way, but this is a simple number. I can handle it. 0 is a problem, and so is 2. 0, I expect there to be an asymptote. Vertical. 2, I expect there to be a zero slope tangent. Let's look at the derivative. Let's see what happens when you're beyond 2, something like that. That'll be 6 minus 16 to the 9 is positive. What happens when I put 1 in here? I get 2 minus 16 is negative. What happens when I put in negative 1? I get negative, negative. So fairly simple. First derivative behavior, decrease, decrease, that's quite an asymptote. And this should be a local, and it happens with 2, that's 4 plus 8 is 4. For the second derivative, if I set this equal to 0, again, 0 is a sort of critical number. Second derivative, I get 32 over x cubed minus 2. So if x cubed is minus 16, so x is negative 16 over a third, or you're a fan of doing it this way, negative 2 third. Okay. So let's map out the cavity here. Something negative. Let's see what we can make out from this. Let's see, when you're positive, this is totally positive. When you're something like negative 1, this is 2 minus 32, it's negative. And when you're huge negative, then this is almost zero and you're back to positive. So it looks like, F is concave up, concave down, concave up. So it looks like in the middle of this, there's no critical number. There's kind of changes happening. Let's see what happens. You have the slope of n in T12. We have an asymptotic zero because, of course, the function is getting very, very large. It's going to positive infinity. It's going to zero from the plus side to negative infinity, negative side. You should be able to see that on the picture. It comes down off the asymptote, decreases, then it goes up, always smile. It's closer and closer to the parabola as we go out that way. On the other side, it's a little more complicated. It's always decreasing, but it's smiling and then it frowns as it goes down the asymptote. So, this. I'm going to flex this again. We'll say it's minus 16 to the 1/3. I'm having. And if you look at these two pieces as they go out, it should get closer and closer to the parabola line. And in fact, this is what I predicted also, as x goes to 0 for the positive side, value of the function is positive infinity. It's going up the asymptote from the right. And as x goes to 0 from the negative side, it's going to the negative. Okay. Any questions? Okay, what else? Hey, you guys, I just got an email from my writer. Quizzes are in block. For you. I just have to go down the part of the grab. Pretty much at the end of it, whatever. Which one did you ask? 9 3B? Oh, this one's easier than my thing. So that's why I put it on there. Be aware of this. So this limit as x goes to 0. sign 3x. We're gonna sign 2x. Okay, how do we do this? Time to use a little, but it's all stuck inside that mess. Fine. Log, tangent, they're both continuous in the domain. So to evaluate the limit inside, you do it outside. That is to say, just do this. Let's just do this as a simpler problem. 0, 0, right? What we call allows us to go. This is cosine 2x times the derivative of the sine. Which is 2/3. The limit of this thing here is 2/3, so it's tangent. The log. This is a theorem that you probably had in 40. Said if you're a continuous function, you can evaluate the limit inside as long as the limits you get here from the continuity, which is not a problem. Because log of 2/3 is some negative number that's not mine. Right. So not too bad. Number 2. All right. So this, so we have the inverse tangent of one over x. This was actually first two derivatives are prime of x. All that here. Minus 2x over x to the 4th minus 2x squared plus 2. That double prime of x is 3. 2. 2 plus 3x. X squared minus 2. On the bottom, you have this. Okay. Here is actually a quick reminder. Anybody remember what the derivative of, you get that crazy square root of one of x plus one. Anybody remember what the inverse tangent looks like? That's the derivative. Function itself. Tangents will be flipped over. Right? So here's an important thing about this. Whatever I draw, I don't care what this blob is, when I take the inverse tangent of it, it has to be between these two horizontal axes. Everything I draw on this thing, no matter how crazy I get, it's always going to have, it's going to be a ceiling of power 2 and a floor of negative power, always. That's an interesting observation. That'll help us. What's the domain? Well, you can plug anything into the inverse tangent, right? It's got the domain of everything. So the domain only depends on what you can plug in here. What do we got to throw out? You got to throw out plus or minus 1. Agree? Now, usually I'm used to this being an asymptote, right? But that's not going to be the case because it is true that when you get close to 1 or close to minus 1, this is getting huge, but the inverse tangent is never big. Okay, so just keep that in mind and see what happens later. Let me do some computations here about the breaks later. I've got these two horrible polynomials here. This one and this one. Okay, first question, does that have any roots? So you can solve this, solve this. Here I get u equal 2 plus or minus square root of 4 minus 8 2. This says no solutions. So in other words, this function x to the 4 minus 2x squared plus 2 never crosses the x-axis. So it's either always positive or it's always negative, because it can never cross the x-axis. Which is it always positive or is it always negative? What happens when you put in 0? Positive, right? If it's 2 and 0, then it's positive. It crosses the axis. So this is always positive. So let me make a note of this one. Here. This thing, always positive. This thing, always positive. Now, what about the other one? The other one can't display it. Let's try to solve. So here, I'm going to let u squared. This is 3u squared minus 2u minus 2. And here I get u equals 2 plus or minus the square root of 4 and 24. So I can get 28. 6. Well, remember, u is x squared. So for me to be able to solve this thing right here has to be positive. So I get x squared 1 plus 37. Minus would work because that'll be a negative number that you get. But I actually did get 2 roots from this. I get both of them plus or minus. So and these are the roots. I'm going to use that later. There it is. Okay, so let's pick out critical. X equals 0 is a critical number. And of course, I've got problems at plus or minus 1. So plus or minus 1 is not the domain. So let's kind of pull what's going on here. Oh, 0 minus 1. Well, look at how convenient this derivative is. The denominator is always positive, and the sign, so the numerator controls the sign. If x is negative, then it's positive. X is positive, it's negative. So happens is increase, increase, increase. It looks like I have a, what happens here? See. It's like down, it's a local max, right? And it should be from 0, whatever I get when I put from 0 to this, that's the inverse tangent of -1. So that's negative power. So I get a little local max. How's second derivative? Well, let's see, I've got these 2 roots here, and then I've got plus or minus 1. Notice this root, 1 plus radical 7. Radical 7 is like somewhere between 2 and 3. So this thing is actually a little bit bigger than 3. So the alpha is a little bit bigger than 1. So minus alpha, minus 1, 1 alpha, like that, where alpha is 1 plus radical 7, 3. When we do the sign analysis here, the denominator is always positive, and the sign is controlled by the numerator. Now, the numerator changes signs of these alphas because they're the roots. So between the 2 alphas, say for example 0, this is negative. And outside the alphas, bigger than the roots, this is going to be positive. So again, one of my ones, something happens. I get up, I get down, I get down, I get down, get up. And I have like points of inflection at the minus sign. Now, what's really got my curiosity for what happens here minus 1, because the argument of this is going to infinity, right? So what happens? Well, you don't understand, you know. Let me draw some pieces of this. At 0 minus power of 4, I have a local max. And something funny happens here. Minus 1 and 1. It's not an asymptote. Let's see what happens. I go to my local max and I decrease down a little. It's undefined. And it's always constant. Everybody agree with me? Let's try what happens. As you get closer and closer to 1, but you're a little less than 0.9, all right, 0.99, etc. This is going to negative infinity. All right, the argument. What happens to the inverse tangent when you go to negative infinity? It's closer and closer to negative power. So plus minus power of 4, this is minus power of 2. As you get here, it's closer and closer to a minus power. And by the way, I think my picture is pretty accurate because what's the limit of the derivative? As x gets closer to 1, negative 2 over 1. So notice on the slope, I get down there. What happens on the other side? Probably a surprise. On the other side, it's increasing. It's always again concave down. Now let me ask you this. What happens to this as x goes to infinity? Get the inverse tangent. What happens to 1 over x squared minus 1 as x goes to infinity? It goes to 0. And the inverse tangent of 0 is 0. So as x goes to infinity, it should get closer and closer to the x-axis. It should go to 0. Let's see what happens on this side. After you leave that strange point of 1, it decreases. It's concave down for a while, and then it's concave up. What happens if you're close to 1? 1.01, 1.001, like that. This is going to positive infinity. Inverse tangent goes to power 2 to positive infinity. So this comes off concave down. And we're it does the mirror image of this. And actually, I don't know. This is what happens at 1 negative. Yeah, this should also be minus 2. Better. That's so that's a good example of notice that you have a denominator going to 0, but you don't really have vertical asymptotes here. It creates a jump. Okay, any questions? Does everybody understand the analysis? Okay, other questions? Yeah, practice, but don't step too late, but seriously, it's a good investment.